Hi, everyone. So today we are going to wrap up Chapter 7 with a video on power. We're going to take what we learned last time and expand on it and do a couple problems. So first, what we have here are some equations for power. So let's write the equation for average power used on the last problem. If you'll remember, last time we used work divided by time to equal power. Okay, this is average power. Okay, we have work over a certain period of time would give you average power, kind of like how average acceleration is change in velocity over time, or average velocity is change in position over time. If there is this work being done over a period of time, where you're going to get your average power. Now we'll use a little calculus to get the instantaneous power equation. So I'll zoom in for this. This will be a doozy. So we'll start with the definition that we have, right? Power is the derivative of work over time. Okay. We know that this is the derivative of work over time because of these analogous relationships, right? If we have a work over time graph, right, then the power here would be the slope because of the relationship it has. Work divided by time would be slope. Same as if this were, right, if this were velocity over time, you'd get acceleration. If this were position over time, you'd get velocity, right? So we can see these relationships working as we go, right, to show that this is slope. So we've got d work over dt. Okay? Now, if we say that work is the integral of force with respect to distance, okay, we'll divide that by time, right? Now, derivative and integral, right? If you take the derivative of an integral, that's just going to cancel out, right? So now we have f dx over dt. So we have force times dx over dt. We already talked about that, right? Dx over dt is right there, just not in calculus form. So we have force times velocity. And this is what you can use to get instantaneous power, right? The power that, say, an engine is generating, if it is using this much force and it is going at this velocity, right? So that's how we can get instantaneous power, force and velocity instead of work and time. So that broadens what we can do there. It gives us another tool in our tool belt. Next, break down the SI unit for power, which is watts. So let's break this down. I'll do that right here. Okay, so watts, okay, that is shown as a W. That's why I put tops on my W's for work, because watts doesn't have one. A watt is a joule per second. Okay, we can also break down a joule. We use Newton meters for work, right? So we have Newton meters per second. And then a Newton is a kilogram meter per second squared times meters per second, like we have there. You can actually see here you've got newtons and a meter per second. Here you have the Newton and the meter per second. So you can see where that is all coming from, right? And then if we expand all of this, this becomes a kilogram meter squared per second cubed. So thank goodness we call it watts, right? That'd be so ridiculous to call it all kilogram meter squared per second cubed every time you had to do a power equation or a power problem. So glad we don't have to do that. Now, we've got a car. Does this car have good horsepower? That definitely looks like a car that has good horsepower, right? So let's see if it really does. We've got a 1,500 kilogram car accelerating from rest to 10 meters per second in 3.0 seconds. So first, we will calculate the work done on the car. So if we want the work, right, we will use work kinetic energy theorem because we have change in velocity there, right? So work will be delta K, which is 1/2 m times v final squared minus v naught squared. So that is 1/2 times 1,500 times our v final is 10 squared. Our initial is 0. And that will come out to 75,000 joules. Okay. That's how much work is being done on the car to travel or to accelerate from rest to 10 meters per second in 3 seconds. Now calculate the average power delivered by the engine. Well, we have average power, right? That is work divided by time, which would be 75,000 joules divided by 3 seconds, which gives you 25,000 joules per second, or watts. So that's average power. Now, how could we calculate the instantaneous power at t equals 2 seconds? So this is going to take some finagling, right? We've got force times velocity. Well, force can be broken down into ma, right? Now, we don't have the acceleration. We can find the acceleration, right? Let's just assume, we'll take average acceleration, right? We'll have to make that assumption that it was constant acceleration. So that would be change in velocity over time. So that would be 10 meters per second divided by 3 seconds. That'll give us 3.33 meters per second squared, right? Now, if that is our acceleration, we can find our instantaneous velocity, right? Because we don't know what the velocity was at 2 seconds. We know what it was at 3 seconds. So if we want to know what it was at 2 seconds, we'd take our acceleration, which is 3.33, and we would multiply that by time, which would be 2 seconds, right? So our acceleration became v over t, delta v over t, and our v became a times t. So if we break that down and our mass as 1,500 kilograms, we will get approximately 33,000 watts, or 33 kilowatts. Not quite to gigawatts yet. So this kind of raises an interesting question, though. Why is our instantaneous horsepower so much larger than our average horsepower? Goodness, I've got the other, it says horsepower right there, reading ahead. Why is our instantaneous power so much bigger than our average power? Well, if we look at power, right, if power is force times velocity, right, actually it'd be more accurate to do velocity and force, right? Okay, if our velocity is starting to increase, okay, it takes more force to travel at that faster velocity. So as that goes, our power here is going to be increasing. So what our average is really just telling us here in the middle, that is 25 kilowatts. But at this time, 2 seconds, oh, well, that's if we did power over time. So let's change that so I can illustrate that, power over time. So as we get further and further down the line here, now we're looking here, this would be 33 kilowatts. If we look at what it was halfway through it, average, right? And then at 2 seconds. So we can see that if you want to find the maximum power of an engine, you need to run it as fast as you can, right? Because we just looked at what it's going part way through, right, at 66 or sorry, 6.66 meters per second. Wasn't even at the full 10 meters per second. So we would need to run it at that to see what is the maximum horsepower of the engine. So letter D actually asks how much power is in the unit horsepower. So 746 watts is in 1 horsepower. If you're going to do power questions and power problems, that's going to be really useful to know. Otherwise, not really useful. But because horsepower is only used when describing engines, it's not really used any other way. But watts is used throughout physics for a lot of things. So, but 746 watts is 1 horsepower. Now, part E actually asks us to sketch the work versus time graph. So if we were to do that, we could show work versus time there. And we'd be able to see that's steadily increasing, right? Oh, actually, work versus time would be parabolic. Right? Yeah, it would be parabolic because work is going to be, in this case, since we're talking about velocity, it's going to be equivalent to a 1/2 mv squared graph. So you would have a parabolic graph for work versus time, which means that if you take the derivative of parabola, you get a line, right? So that's why our power line that I drew, power versus time, would be linear. Now, if we wanted to find the horsepower of this engine, right, does this car have good horsepower? That was the question. So let's look at that. What we could do is we could take those watts and divide them by 746 to get horsepower. So if you do the division here, 25,000 watts comes out to about 33.5 horsepower. And 33,000 watts comes out to about 44.2 horsepower. Now you might think, okay, 40 horses, that's a lot of horsepower. But a Toyota Prius, which is mocked commonly for its horsepower, just for being a Prius in general, but the Prius has about 120 horsepower. So this car has about a third of the horsepower than this Prius. Now, if we wanted to look at how much power it has maximum, right, at 10 meters per second, let's say that is, that's the most power it can give. We could say that we know it can accelerate at 3.33, right? So we have ma times v, that'd be 1,500 times 3.33 times 10. You get about 50,000 watts, 50 kilowatts, divided by 746, you get 67 horsepower. Yikes. So that's not great. But I mean, I assume 10 meters per second is not the maximum speed of this car. If it is, that's a really slow car. That's a golf cart, I think, if I'm doing that right in my head. Anyway, so that's how we can find power of an engine in several different ways, right? Calculate the work. You can use work kinetic energy theorem. We found average power. We found instantaneous power. We were using several graphs to analyze the situation, and we can find horsepower from the watts that we had before. Okay, now let's talk about elevators. This elevator has a mass of 1,000 kilograms and can carry a maximum load of 800 kilograms. Has a constant frictional force of 4,000 newtons resisting upward motion, so we know it's going up. Draw a free body diagram for the forces involved. So let's see what we've got. We've got tension, right? Tension in a rope is pulling it up in a cord. You've got, let's just say mass total times gravity. Let's say it's 1,800 kilograms, maxed out, right? And then we have friction force of 4,000 newtons. Okay, so that's our free body diagram. Part B. Write an equation for the instantaneous power delivered at any velocity to produce an acceleration. Okay, so let's see what we've got. We've got T minus mg minus friction equals ma, right? That's going to be our summation of forces. Now, to do power, you can do summation of forces times velocity, right? We need to know the total unbalanced force acting to see how much power there's going to be. So if the tension is the one driving this power, right, delivering the power, you add everything else to the other side. You have ma plus mg plus friction. That can simplify to m times a plus g plus friction. Okay. So that's what we would get for our summation of forces. And then to get power, okay, you take the summation of forces and multiply that by velocity. So you'd have friction plus m a plus g all times velocity. That would be the equation that you end up with. Okay, to give you, depending on any velocity, right? Any velocity producing some acceleration in the elevator, that's what you would get, right? Now, part C asks us to calculate the minimum power necessary to engineer the elevator to cruise at a constant speed of 3 meters per second. It asks which mass should you use. So we will max load the entire elevator, okay? 1,800 kilograms. So if we look at power, okay, we don't have acceleration, so we have friction. That's a really bad friction. Let's fix that. We have friction plus our mass. There is no acceleration. It's going constant speed, so there's just mg all times our constant velocity. So that would be 4,000 newtons of friction plus 1,800 kilograms times 9.81 for gravity, all times 3. And that's going to come out to about, what is that, 65,000 watts or 65 kilowatts. Okay. So that is the kind of power we're dealing with here. Now, we were able to use the information from a free body diagram to find the instantaneous power if we were given the velocity that was traveling, right? We need acceleration and velocity. Here there was no acceleration, but there was velocity. So we were able to say that there was some power that was, keeping it at that constant speed. However, last slide of the chapter, this paradox. In the previous problem, the motor delivers power, yet there is no change in speed. Right? Constant speed, no acceleration. A student now claims that if the change in kinetic energy is 0, then the kinetic energy work theorem says that the work must be 0 also. And if the work is 0, then the power is also supposed to be 0. So how do we explain this? So let's break this down what the student is saying, right? So the student says that because of the work kinetic energy theorem, right? If the change in kinetic energy is 0, that means that work should also be 0, right? And if we're talking about work over time, right? If the work is 0, and we try and find the slope of that line, remember power is the slope of this graph, that would also be 0. Slope of 0 is 0. So where are we getting confused here? Well, we have to think about all the things that are going on, right? Because first, work kinetic energy theorem doesn't tell you everything going on energy-wise, right? So first, we have to overcome these forces, right? There is friction and gravity that must be overcome. Because if you're going to move something at a constant speed and there are resistive forces, it's going to take power to travel at that constant speed. because you have to provide that force to overcome those. Now, if you're going to overcome them and cause an acceleration, then you will have even greater force, right? Because you're going to add that acceleration to your G, resulting in a higher instantaneous power. Now, we also need to talk about the energy involved, okay? And we will talk about this energy a lot more in the next chapter. But the kinetic energy, yes, there is no change in kinetic energy, but as we rise an object, okay, we're giving it something that's called gravitational potential energy. Okay, it's kind of like if I were to raise my pencil, right? Raise this little Apple pencil. If I raise it up, I have given it gravitational potential energy, because if I were to drop it, right, then it would just fall to the table, make a big loud noise. But that gravitational potential energy turns into kinetic energy, right? So what you're doing as when you raise an object in a gravitational field, you are giving it energy. It's given potential energy. And that potential energy is often converted to kinetic energy once it is let go and released to fall or ride down a track or swing on a pendulum, things like that. So the reason there is power is because there's so much resistance that actually needs to be overcome. Plus, it takes power to convert that kinetic energy into potential energy, which is exactly what that elevator is doing. All right, so that's all we have for chapter 7. Next chapter, chapter 8, we will continue this discussion and we'll go over conservation of energy.